Hello, thank you, Leah, and welcome everyone virtually, or welcome virtually to Battersea, where I'm live broadcasting this webinar. So I'm going to talk today a bit about plastic recycling and some of the challenges and some of the things that we're doing at Imperial to deal with this. And I mentioned to Leah when we set up this presentation, it's a little bit high level in the sense that I'm going to talk about half of it about the challenges that we are attempting to address, or the ones that I see as the ones that we are most capable of addressing with technology developments, particularly in molecular science. And then the second half of it, I'll give you an overview of some of the activities at our project in Imperial, with a little bit of a bias towards the ones that I'm involved in, because of course they're the ones that I find the most interesting. And there won't be time at the end for me to give an in-depth bit on chemical recycling, but I prepared it just in the very off chance that I go really fast. So at the start here, I'm going to give some background on plastic recycling and the current challenges and just how bad the situation is. It's not intended necessarily to scare people, but I think it is quite important to always keep a perspective on how multifaceted this challenge is. I always start by saying, or admitting, that I got the idea for these slides and these slides themselves from Charles Romain, who's a research fellow in chemistry. And I saw him give a Pint of Science talk back when the world still had things like, Pint of Science. And I said, his slides were so fantastic. And so whenever you see your ex-postdoc give a fantastic background section, you have to steal the slides. And so Charles was kind enough to let me do it. All the wonderful statistics on London buses. And so I always think, we've been working on plastic recycling for a couple of years, but sort of in the background. And then David Attenborough did this presentation on Blue Planet for BBC. And everybody all of a sudden got quite up in arms about how bad the plastic pollution problem is. And so I think it is important to note that this has been a problem that has plagued us for decades. But it took sort of a popular uprising caused by a television program to really bring it to the forefront. And sadly, that is often the case in science. We're working on challenges at a global scale, climate change or pollution or whatever. But it's that very visual connection to the public interest that really helps push solutions through to the forefront. And as a result, I think directly of that program, I have never worked on a project or a topic that's more universally supported. From the public to the researchers to the students, all the way through to the companies that are making products. Everybody is really keen to have better solutions to plastic waste. So, how bad is the problem? And, I mean, you can give numbers on anything, but it's useful to start thinking about what these numbers translate into. And the easiest one is that roughly 10 million tons of plastic every year ends up in the oceans. And that is an absolutely staggering amount, 10 million tons. And as Charles helpfully calculated out, that's the equivalent mass of 770,000 London double-decker buses every year that ends up in the ocean floating around. And according to recent research, only about 1% of it stays on the surface, and the other 99% sinks to the bottom and probably causes even bigger problems. Roughly 80% of that is what we would refer to as a land-based plastic. So that is stuff that was thrown away on land, usually finds its way into either rivers or lakes, and then travels out into the ocean. So 80% from land, and the other 20% from ocean-based activities. And we always focus on the ocean. That gives us this huge global number, and I think that's very important. But it's also sort of a local problem. Every year, 300 tons of plastic are cleaned out of the Thames. So that's the amount that we stop from going out into the ocean. And so that's 24 London buses that we rescue just inside the city of London. And I live, as I said, in Battersea, and so you can actually see them out the window, walking up and down and picking up plastic that washes up at low tide. And it's quite a frightening to think that we can rescue 300 tons just in one city. The other 20%, so it's always good to say, well, okay, 80%, what's the other 20%? And the other 20%, a little bit more what you would expect plastic waste to end up in the ocean. So that's stuff that started out in the ocean. So either offshore platforms or losses during shipping or fishing lines and that sort of thing. But still, it gives a pretty good distribution of how big the problem is and just how much of it's floating around. I love this. This is easily my favorite article ever. In 1990, this is 1996, but it was 1992. There was a cargo ship off the coast of China that lost a shipment of rubber ducks, 28,000 rubber ducks. And they're still out there. And so because of the serial numbers and what, they could track the rubber ducks and could watch them move around the world according to where they were found at various times. And the article was in 2017, and they could still find the rubber ducks floating around. And as I said, they were lost near China, but they've been found off the coast of the UK. And that's an absolutely incredible journey for pieces of plastic to take. And while 28,000 rubber ducks isn't much in the grand scheme of 10 million tons a year of plastic, it highlights just how mobile a lot of these plastics are. And Imperial, of course, the Grantham Institute did the Plastic Adrift project, which, if you've ever been to one of the Imperial festivals, they have an absolutely fantastic display where you can play around and you can drop plastic in various places and watch it move around the world, all over the place. And there's a pretty good current system between the coast of Europe and the coast of the United States in particular, and you can sort of see how plastic will travel back and forth and spread out across the Atlantic Ocean, and it takes about 5 years to move around. This is one of my favorite tasks I do every time I talk about waste plastic. I update the slide. If you do a Google search on plastic, not on waste plastic, if you do a Google search on plastic, the news has started out about maybe 3 or 4 years ago. It was universally quite bad. It has gradually started to get a little bit more positive. And I take that as a nice sign that we're starting to address the problem rather than just complain about it. But still, there's a lot of headlines, there's a lot of interest, there's a lot of articles, there's a lot of talk, even during coronavirus, which you can see creep into one of the top 20 headlines that I've shown here. But there's a lot of public awareness about plastic waste and in different ways that we can tackle it. And we're starting, I think, to move the debate into slightly more esoteric areas, which I think is good. You can see the article on the right-hand side there. I don't know if you can see my cursor moving around, but about biodegradable versus recyclable plastics. And I'm not going to talk about that today, but it is a trope that I often go off on. And so perhaps if you taunt me in the Q&A session, I'll give you an opinion there too. The reason that I find this quite interesting is plastic, certainly in the public, plastic has become quite vilified as a result of this waste problem. But plastic, of course, is one of the most incredibly useful materials that we've ever produced. And I often say that the production of polymers was probably the greatest feat of chemical engineering in history. And you look at the development of these sorts of things over time. Plastics have replaced more and more of the materials economy since they first really started to be introduced between the 1920s and the 1950s. And of course, they have an extremely positive effect on certain aspects of our economy. The biggest one, of course, is about weight. So the big advantage of plastics over other materials is that they're very strong for their mass. As a result, at the moment, plastics make up, on average, about 15% of an automobile. And if you think about the weight difference between plastic and aluminium, that has an enormous impact on reducing vehicle weight and on increasing fuel economy. And whether we go to electric cars or hybrid vehicles or hydrogen cars or whatever, the lower the weight, the less the impact of driving on the environment. Well, I think this is very important, and things like carbon fiber reinforced plastics have been essential to replacing steel and aluminum in aircraft. And those sorts of developments could be seen throughout the entire supply chain and all of the materials that we produce from plastic. So as a material, it has absolutely fantastic properties, and we've been taking advantage of these to solve environmental problems, such as climate change, such as the pollution and damage caused by other human activities like mining. Oops, my presentation's a little stuck there, sorry. And so we've become quite reliant on plastics, and depending on exactly how you define plastic, and people have different definitions, but there's somewhere between 310 and 360 million tons a year of plastic produced, which is 25 million London buses. And it has a lot of applications in many, many sectors. And I'm going to come back to packaging, which is the largest use of plastics. It's about 40 million tons a year. It's the focus of the program that we have here at Imperial College that I'll speak about in the second half of this presentation. But of course, packaging is not the only use of plastic, and you can see the broad range of things from automotive to agriculture to, of course, electronics, where plastic plays an essential role due to its moldability. Oh, well, okay. And I mentioned earlier the low cost and the high strength to weight ratio being key factors, but there's also a lot to be said for versatility. And because thermoplastics in particular are so easy to mold, this is a feature that we have taken advantage of in creating a variety of products, including a lot of flexible products. It's also easy to make transparent plastics, and I often talk about polyethylene terephthalate. It might be the most remarkable, I guess, single material or single component material that we've ever made in terms of its toughness, its durability, its barrier properties, and yet it's still transparent. Those sorts of things are very difficult to get with other materials. And so as a result, a lot of the explosion in plastic waste has developed from an explosion in our use of plastics, again, for fairly good reasons to begin with. There's a little bit of delay on my screen, so I hope you guys are seeing this. And that sort of dependence on plastic is what has led to those environmental issues. At the moment, plastics consume roughly 6% of our fossil resources. Since somewhere between 90 and 92% of our fossil resources are burned for energy production, so either electricity or transport, that's 6 of the other 8 to 10% of a barrel of oil that ends up in plastic. Polymers, the primary polymer market, are about 70% of the end-use chemical market by mass. And so roughly 70% of petrochemicals end up being polymers in some respects. And of course, you can translate that across into a percentage of our carbon budget. And at the moment, that's somewhere between 4 and 6%, depending on how you look at it, of the oil and gas production, and it's about 1% of the total carbon budget for the planet. And the Ellen MacArthur Foundation, of course, has done a wonderful job of raising awareness in this area, and a lot of that's come from gathering what I refer to as very, very scary statistics. At the moment, the ratio by mass of plastics to fish in the ocean is 1 to 5, and by about the year 2050, at the current rate of pollution, the ratio of fish and plastic in the ocean will be equivalent. So there will be as much tonnage of plastic floating around as tonnage of fish. I don't believe in my entire life I've ever heard a scarier statistic on pollution. Because of the increase in renewable energy, coupled with a less than rapid increase in the production of renewable materials, it's projected that the share of global oil consumption going to plastics will increase from the current 6% that I mentioned a moment ago to about 20% by 2050. So we're reducing the amount of oil that we're going to use for primary energy. We are projected to increase the amount of plastic that we're going to produce. And that, of course, means that while right now, plastics make up a tiny fraction of the carbon budget for the planet, that's expected to increase by more than an order of magnitude in the near future. So I think it's very important when thinking about the amount of plastic that's made to remember that, first of all, it's a very durable material, so it's with us for a long time. And second of all, as demand for it increases and demand for other things decrease, it's going to take on a larger and larger significance in terms of our materials economy. I think the biggest worry that I have, and this has been borne out, I was quite scared about this in roughly the early part of 2019, so it was January of last year. It was at the World Economic Forum in Davos, and all these talks on waste plastics and things that people were going to do about it. And half of them I thought were crazy ideas. And they were talking about all these single-use plastic bans in Europe, and I was terrified of that. And I said, okay, a single-use plastic ban in Europe right now would be a huge mistake. And of course, we immediately got the single-use plastic ban in Europe. And the reason that I thought it was going to be a big mistake is because at present, we don't have a better idea. So what exactly are we going to replace all this plastic packaging with? And the most obvious materials that we will fall back on are paper, glass, and metal. And of course, McDonald's immediately went and replaced all of the plastic straws with paper straws. Those paper straws can't be recycled, so they're a single-use material also. And the environmental footprint of paper making, so from the craft process especially, in terms of pollution to the environment and energy input, is higher than the amount produced from plastic. So from a point of view of primary pollution, paper is a bigger culprit than plastic. And so replacing plastic with paper, while you do get the benefit of biodegradability, on the flip side, you increase all of the pollution going out into the environment and you exacerbate other issues. As far as plastic to glass, this of course is obviously a step backwards in time, but it's also somewhat a step backwards in terms of the environment. So this one's a little bit more controversial and debatable, but because glass is heavier than plastic by about 42%, shipping glass bottles around instead of plastic bottles around will contribute to a very large increase in CO2 emissions. And so again, this is a trade-off. Also, of course, the CO2 footprint or the carbon footprint of glass is extraordinarily high, much higher than plastic. And in theory, a plastic bottle should be more recyclable than a glass bottle because of the reduction in possibility of breakage. And so transitioning from plastic to glass, while somewhat more acceptable from an environmental standpoint than shifting to paper, isn't likely to be a very good answer either. And I didn't put it on the slide, but don't even get me started on the proposals to shift from plastic to metal. I cannot think of an activity more damaging to the planet that humans do than mining. It's an absolutely crazy industry in terms of, it's digging holes in the ground and pouring acid into them. What could possibly go wrong with that? So increasing these sorts of products at the expense of plastic, while it reduces the ocean plastic problem, will have knock-on effects in terms of especially carbon footprint, global warming, and also primary pollution to the environment. So the project that we have undertaken here at Imperial College, which has that lovely, very long title that we couldn't come up with an acronym for, is a big multidisciplinary project looking primarily at plastic packaging. And it involves 7 different departments and 17 investigators, well, 16 of them in Imperial and 1 King's College. And so it's actually quite a nice little IMSE in a bottle type of program involving a large multidisciplinary team looking at various aspects. I'm going to give you a very brief overview of the activities at the moment in order to sort of give you a flavor of what we're doing. And I'm happy to expand on that at a later time if you wish. So there's the team over there on the left. Managing a team of 17 academics is exactly as easy as you might expect it to be. The departments involved are chemical engineering, mechanical engineering, civil engineering, chemistry, design engineering, materials, the Center for Environmental Policy, and aeronautics. So it's a huge team covering a lot of different aspects. And as I said, I'll take you through about 4 or 5 of them right now. This was sort of our inspiration for the program, was about that loop in the middle of this screen. And so this shows, it's again from the Ellen MacArthur Foundation, but it shows how linear the plastic industry is. And so in 2014, 2015, only 2% of plastic was involved in what we refer to as closed loop recycling. And so 98% of the plastic in products that were entering the market were from virgin feedstocks, so plastic that was made for that project. Some of the scarier things I'll point out on this slide. So we incinerate 14% of that plastic. I think that's fine. 14% of it is collected for recycling. So the amount that is burned and the amount that we actually attempt to even recycle are about equivalent. 40% of it is sent to landfill, which is probably too much, but at least it doesn't do too much harm there. Some microplastic issues, but at least we know where it is. 32% of the plastic that is produced at the moment, we actually don't know where it is. Now, a large portion of that is what you might refer to as still in use. It is estimated that somewhere between 20 and 30% of all of the plastic that was ever produced is still in use in its primary function, so it's still being used as intended because the products are so durable. The rest of that, we actually don't even know where it is. And so this is where the plastic pollution problem originates, is that 32% that we actually have no idea what happens to it. The other scary thing is that of the 14% that's collected for recycling, 2%, so 1/7 of that stream actually ends up getting recycled. 4% of it is lost during the recycling process. So twice as much plastic is actually lost in recycling as is recycled. And then 8% of it goes into cascaded recycling. So it's not actually reused in the original project, but in something else. So those are quite scary. And we built our program sort of off the back of the waste pyramid. And so thinking about reducing the amount of plastic in products, and that's a big task in design engineering. Reuse, so how do we reuse, and the plastic bottles, the reusable plastic bottles are a great example of this. How do we reuse materials for the exact same purpose again and again? And then a big project on recycling, so mechanical and chemical recycling, which is what I'll talk about in a moment. And of course, there are other things that you can do. And you hear a lot about people doing downcycling, so using old plastic material to make other things like building insulation. That's nice. But anytime you do downcycling, of course, you increase the input back into the system. And so you have to replace those primary products as the demand for those materials increases. And so while downcycling is better than throwing things into the river, it isn't an ideal end use for materials. This is, I always point this out because this is actually very, very scary. So this slide is very useful because it tells you what different plastic materials are used for. But there are actually 10, or in some countries 13, but in the UK there are 10 categories of recycled plastics. Here's the 7 that are basically recognized worldwide. I live in the center of London, so in the center of one of the largest cities in the world, one of the largest cities in Europe, certainly. And we only recycle the first 3 categories. And so depending on what borough you live in, what council you live in, what country you live in, even though it's got the little triangle thing with a number in the middle, not all of those little numbers actually are recyclable in that area. And so it's actually something you have to do a bit of digging to find out what is and isn't recycled, depending on where you live. I thought that was actually quite frightening, that even though you think you put something into the recycling bin and it's going to be recycled, actually it might not be. This is what a waste plastic stream looks like, by the way. And anytime we talk about these municipal solid waste to whatever projects, this is always what pops into my head. I mean, basically a giant mountain of lots of stuff, different plastics, different sizes, with lots of other things like paper and metals and dirt and all sorts of things in there, dyes and additives and all of these things. And so it's a very heterogeneous waste stream, and it's a very heterogeneous material to begin with. And so this is why the challenge of recycling plastic is so great. With the exception of plastic bottles, which are roughly the only single polymer material that we use in packaging, everything else is always either a mixture of plastics or a mixture of plastics with other things, or both. And great examples of this are in the food packaging that we're working on in our project. I mentioned the plastic bottles, and like I said, it always ends up being a Coke bottle for some reason. Their branding is so powerful that you basically can't talk about plastic bottles without using Coca-Cola. But even that, traditionally, has been a multi-plastic material. So the bottle itself is just a PET bottle. And as I said, this is why it's so recyclable. It's a single plastic, single material, fairly high purity. But we often use labels that are either low density polyethylene or PVC. We seal it with a polyethylene seal, and we use a lid that's normally polypropylene. And that's why the lid and the ring have to be removed before you can recycle the bottle. The lid, the ring, the seal, and the label all have to be removed from the bottle before it can be recycled. I mentioned that it's the most recyclable material, and that's true. Roughly in Europe, roughly 30% of plastic bottles, PET bottles, are recycled. It's actually quite a low figure. So it is as high as 90% in some areas. I think the highest at the moment is Germany, and it is, like I said, as low as 30% in other countries. So that's a relatively simple piece of packaging to recycle. Something a lot more complicated is a crisp packet. And for reasons that will become obvious in a moment, we have to use a brandless crisp packet to talk about crisp packets. But these are absolutely incredible. And a crisp packet, or something like a candy bar wrapper, often have between 7 and 11 different layers. And those 7 to 11 different layers contain between 4 and 7 different plastic materials, laminated on top of each other. And each of those laminated layers normally has an adhesive in between it to hold it together. And then there's the ink for the printing, and, all of these things on the outside. So we have all of these different plastics. We have these compatibilizers and additives, and then we have things like metal layers. I mentioned aluminum as an oxygen barrier. Sometimes we also use titanium oxide and even nickel at times in food packaging in order to protect it. There's also often cellulose layers, so you'll see paper layers on the inside to touch the food. And each of these layers serves a distinct purpose within the packaging material. But as you might expect, separating all of those layers off a crisp packet is a virtually impossible task. And so as a result, this sort of multi-layer food packaging has effectively a 0% recycle rate. There's some push at the moment to have an increased collection, as the collection percentage, last I saw was about 20%. But that's mainly for energy recovery. So the recycling rate is very, very low. And there are a lot of different approaches that have been proposed for this. We've been looking at sort of combinations of mechanical and chemical recycling to deal with multi-layer plastics. They dovetail quite nicely because the strengths of one and the weaknesses of the other tend not to overlap. Mechanical recycling has got a lot of really positive effects to it. Primarily, it's easy, very low energy input. So it's probably the lowest energy recycling option. Chemical recycling has the advantage that it restores the polymer back to its virgin state. And so you can depolymerize a polymer and then repolymerize it. And of course, you end up with the exact same properties that you started with. Whereas mechanical recycling, every time you mechanically recycle or even just melt reprocess a plastic, you lose some chain length. And so as a result, the properties decrease over time. This is quite important in food packaging because of course the standards are very, very stringent in terms of what properties can and cannot be tolerated. And so those two types of approaches fit well with each other. And in our program, we've been looking at ways to fit them together in order to increase the amount of material that can be recycled, mechanically recycle what you can and chemically recycle what you can't. This is the only time I'm going to talk about ionic liquids, probably, is in the next 2 minutes, but this is from the Department of Chemistry. It's a project from Aggie Brett looking at chemical recycling of plastics using ionic liquids. And the advantage there is that we're looking at a low energy process for taking PET or PLA, or in chemical engineering, we're looking at polyamides like nylon and trying to recycle the monomer in as energy efficient a manner as possible. This, of course, is very, very important because with a lot of chemical recycling technologies, you end up with a higher energy input than the original polymer had. And so you would literally be better off from an energy standpoint, burning the waste and making more plastic. And I always think that in terms of challenges in this space, a really good life cycle assessment that looks at different options is something that was sorely needed, because it's not always obvious that a recycling technology can compete favorably with incineration. And I think at a minimum, incineration makes the problem go away. And we should be doing recycling technologies where we think we will have environmental benefits over incineration, not where we think that it will give good PR. In chemical engineering, in my group, in collaboration with Alex Brogan at King's University, King's College London, we're looking at biochemical recycling. And this was sort of inspired by the work primarily at Portsmouth, looking at the PET degrading bacteria that were found in Japanese landfills. Biological recycling of things like polyesters or polyamides are very selective, which is quite attractive. The problem is they're very, very slow. And I've shown the graph there, the difference between chemical and biochemical recycling as a function of temperature. And up to about 40 degrees, they're roughly equivalent to each other. And then, of course, after that, you can keep heating up a chemical process to make it go faster, but the biological process falls apart because the enzymes start to denature and lose activity. So what we have done is we've made modifications of proteins so that they're stable at very high temperatures. And the graph on the right shows that we can shift, my axis got cut off, but shows that we can shift the temperature of an enzymatic process from 50 degrees to about 200 degrees, which allows us to sort of access the right hand of that Arrhenius plot in the upper left. And so that sort of gives us an idea of where these different processes have advantages and disadvantages. And I mentioned that mechanical recycling is always the lowest energy cost. It's also the easiest one to implement. It's something that we do right now. It's mostly limited by sorting technologies. It doesn't cost very much. These are all great advantages. The chemical technologies, of course, sort of sit in an intermediate space where the energy cost is a bit higher, but the advantage is that you get the exact same material back. We know how to scale chemical processes very well. We don't yet really know how much they'll cost, and we don't yet really know what the environmental impact of chemical recycling is. But nicely, you can get a full restoration. And of course, there's also pyrolysis or thermal recycling, and as I mentioned, biological recycling, which is still in its infancy. And there's some other activities at Imperial as part of this project, and I'm showing a few here. At the top there is research by Kunyang Lee in aeronautics of making composites from different waste materials. And sort of the flagship of that is looking at composites of recycled cellulose, so recycled paper with recycled plastic. And the team in aeronautics was able to make composite materials from those two wastes that were stronger than the original materials that they're intended to replace. And so that is sort of an upcycling from waste to higher end materials. And they use two waste streams in order to do that. In CEP, we've had a big focus on policy analysis and development, because one of the biggest barriers to implementing more plastic recycling is that there is a lack of appreciation, I guess, for exactly what the knock-on effects of a lot of these technologies are. And people get excited by seeing things in the media, including policymakers get excited by seeing things in the media that perhaps are red herrings, because they either don't address very much of the plastic recycling problem, so they pick on very small streams, or as I said, they're downcycling technologies, and so they don't actually impact the material input in the first place. And so it's recycling as an add-on rather than recycling to replace primary production. And so Arturo Castillo in Center for Environmental Policy has done quite a bit of work. I mean, he's done some wonderful policy stakeholder events, and also Leah mentioned the policy paper in order to try and inform public opinion and inform government and policymakers on how we can integrate some of these new technologies. And finally, you know, I find this whole thing fascinating. Marco Orsicchio and Peter Childs in design engineering, looking at sort of the systems design and business models, and how do you incentivize both consumers and businesses to increase plastic recycling. And Marco in particular has done a tremendous amount of work in trying to get people to rethink the way the economy works and the way that people interact with plastics. And it's absolutely fascinating pieces of research. And some of it has thrown up unintended consequences, like I mentioned earlier with the paper straws. And sort of how do we design systems such that we don't accidentally shift the problem from one area to another. And the final thing I will mention, because as I predicted, I always ramble on forever, and so I run out of time. But the final thing I'll mention, I'm very proud of this. One of my PhD students who was working on this project while we were doing textile recycling, polycotton blends, so mixtures of PET and cotton. I learned a couple of things. I learned that actually plastic bottles are not the biggest use of PET in the world. Actually, it's only about 30%. There's actually more textiles using polyesters than food packaging. I was shocked by that. But the second thing, and by the way, the recycle rate in the textile industry is so small as to be insignificant. But the second thing that was quite interesting was, while attempting to do the fiber recycling, so the polyester recycling, Ida Rafat accidentally developed a process for dye recycling. And as far as we can tell, this is the first proposed dye recycling technology that doesn't involve a phase change. So in other words, she can extract the dye from one piece of fabric and transfer it into another piece of fabric without doing anything, with the magic of solvents. Ida and I recently launched a company. There's a website down there, Dye Recycle, very original name for a company that recycles dyes, looking at pre-consumer textile waste as a primary product. And so I think, yes, that is the end of my presentation. And so from here, I'm happy to answer questions. I see there are some, so I'm going to try and open the Q&A. I'll give you guys a moment to, of course, recover from from all of this excitement, and then I'll answer some questions. Okay, so first question I see is from Annette. She says, yes, I would like to hear your opinion on the topic of biodegradable versus recyclable plastics and which ones are better for the environment. Oh my, that's a loaded question, Annette. So it's a great question, where biodegradation fits into this. So I'm of mixed opinion on biodegradability. There's something to be said for knowing what a material is going to do in the environment. And PET is a great example. If PET was biodegradable, which fortunately it's not, it takes I think it's 10,000 years to biodegrade. If PET was biodegradable, the first thing it would do would be to emit ethylene. Ethylene, of course, is one of the most potent greenhouse gases that we know of. It's also quite toxic, but so fortunately for us, PET doesn't biodegrade because the biodegradation products would be absolutely fantastically nasty. So in that sense, it's good that it locks up the carbon. And a second advantage of having things not biodegrade is that the carbon that's in them is locked up. And so I always think, first and foremost, the problem with plastics is not that they don't biodegrade. The problem is that we keep insisting on throwing them into the rivers and throwing them into the oceans. So the problem is that we don't control them very well. Now the question of biodegradability sort of gets into that area of human behavior. So if we really think that we can't control ourselves and we can't figure out a way to collect all of the plastic materials that we produce and put out there, then biodegradation is a nice backstop, because at the very least, at the end of it, it will go away. The big problem I see at the moment is that there is virtually no appreciation for, or no understanding for what a biodegrading plastic will do in the environment. And so we actually don't have a very good idea of how much microplastics they will produce. By my estimates, it's probably more nanoplastics that you get from biodegradable plastics in the short term than you would from non-biodegradable plastics. And then in the long term, of course, then they go away and produce CO2. And so that's sort of a good thing. And so I would say it's a bit of a trade-off between, you know, if you're very pessimistic about our ability to change human behavior for the better, having biodegradable plastics is nice. If you're optimistic about changing human behavior, then I would say it's less necessary. So I hope that's sufficient. Oh, I think I did that wrong. But anyway. So the second question, where would you suggest to look to find out more about biodegradable versus recyclable? Actually, that's a good, actually I can't answer that. I don't know. There's a lot of debate out there, some of it informed and some of it uninformed. And I think the problem with bioplastics in general is that we can't settle on a definition of what makes a bioplastic, what makes a biodegradable plastic. We know what a bio-based plastic is, but we don't necessarily know how to define biodegradability. So, you know, how biodegradable is it, and whether industrially compostable qualifies as biodegradable, or whether it has to biodegrade sort of in the ocean. And again, as I said, depending on the mechanisms that are employed during the biodegradation, it could at times be more trouble than it's worth. Some materials are quite good. But I would say my caution to everyone is don't automatically assume that just because something biodegrades that it's okay. There needs to be a full appreciation for exactly what happens to it in the meantime. Okay. Algae. The next question is about algae. Oh, sorry, I lost it there for a second. Will help as an alternative material. This is a very good question. There are two problems with algae, neither of which has currently been solved. And that's not to say they can't be solved. So let me say it front. I'm not saying it's impossible. I'm saying at the moment. We have two problems. The first one is that we do not have an idea of how to scale up algae production. And you look at who has been attempting to scale up algae production to date, and it has mostly been large, traditionally petrochemical type companies that specialize in scaling up energy-based technologies, and they have all failed. And so algae has to date defied our attempts to control its large-scale production. I think algal-based materials are a nice compromise in the sense that they are sort of the lowest likely environmental damage that you can come up with, right? I mean, basically natural materials, lipids and bioplastics and things, which is good. On the flip side, in order to produce the materials, of course, you have to dry the algae. And even dewatered algae is about 90% water. And so if you start talking about replacing plastics with algae, that is definitely a trade-off between sort of petrochemical usage and CO2 emissions, because algal-based materials are likely to be very energy intensive to produce, at least in the short term. So I think if you want a nice research area, try to figure out how to make an algal-based material at scale with a low energy input. That would be really a huge breakthrough if somebody could do that. So there's I don't want to take too long here. So there's a question on what proportion of all plastic we use today do you think can be substituted by biodegradable substances? Oh my! And what proportion of petrochemicals as feedstocks can be economically substituted by cleaner feedstocks? At the moment, the answer is probably zero. This comes back to the problem, the hardest problem to solve that I have ever seen, which is you have to use air quotes here, the hidden subsidies that exist in petrochemicals. As long as we value the emission of carbon dioxide at zero, so as long as we tacitly state that it costs us nothing to emit CO2 into the atmosphere, it is going to be pretty much impossible to replace petrochemicals with anything. Because the materials themselves, all right, we've already developed an entire industry around exploiting them. And so breaking into that at scale is going to be very difficult. And Paul Mines, who's the CEO of Biome, which is a bioplastics company in the UK, gives a great analogy for what the problem is. He was talking about the largest PLA plant at the time. This is last year. So the largest PLA plant in the world, I think, was 50,000 tons per year. He said the average polyethylene terephthalate, so the average PET plant, is about 1.2 million tons per year. And so as long as you are attempting to fight a behemoth making 1 million tons with something that makes 50,000 tons, you cannot win on economic grounds. And so I would say as long as we do not put any cost on the use of fossil resources, whether it's for CO2 emissions or because of recycling or environmental damage from oil drilling or whatever, as long as there is no cost associated with the environmental damage caused by fossil fuels, I don't think they can be beaten on economics. That is an unfair advantage that they have enjoyed for, in my opinion, far too long, but there you go. So somebody asked about microplastic pollution. So I can talk about it in a little bit because I've been getting involved in a project with Alex Porter in the materials department, and also with some colleagues at the University of Bristol who work on ecology. And it's really an interesting thing. So microplastics, the most prominent one comes from textile fibers because it's the one that we understand the flows of the best. So it's the easiest one to talk about. So when you wash polyester material in a washing machine, some of the fibers will shed off. It's quite natural, right? So it's a woven fabric. So some of the fibers are released in the washing machine. And they go through, of course, into the sewer, which is where wastewater from washing machines go. They go into wastewater treatment, and wastewater treatment, they go into the anaerobic digester, which is a microbial bioreactor that eats up the organic material. And of course, they don't biodegrade because polyethylene terephthalate, PET, is not biodegradable. And so they pass through into the waste material from that, which is called sewage sludge. It's a very attractive name. And that is used as a land spread. So that material is spread on the soil as a fertilizer. It's actually a very good fertilizer. And the microplastics that have shed off in the washing machine go all the way through this process and go out into the soil. And then they have a very negative impact on soil microbes. And of course, soil microbes are the organisms that fix nitrogen, and actually sometimes other things, but fix nitrogen out of the atmosphere. And so as we lose soil microbes, we lose soil organic matter, and therefore reduce the viability of farmland. And so basically, microplastics make it harder for us to grow food. That's pretty much the biggest problem. They poison the soil. Should you be buying cans of Coke or bottles? Oh, that's a tough question. Yeah, so the first part of this question, assuming both are collected for recycling, should I be buying cans of Coke or bottles? So this is that first part is very, very important, assuming both are collected. The energy required to recycle aluminium is higher than the energy required to recycle PET. But the recycling process for aluminium has a higher yield than the recycling process for PET, so it has less losses. So if you're interested in saving the environment from pollution, buy cans. If you're interested in saving the environment from climate change, buy bottles. And I'm sorry, I can't give you a better answer than that because it is literally a trade-off between multiple effects. I would say on a personal note, as I already mentioned earlier in this presentation, mining is a terrible industry. I mean, they're all good people. I've met some of them. They're all good people, but you know, as with oil, we're drilling holes in the ground to extract resources, and there's a big cost that's paid by the environment from those activities, no matter what they are, whether it's mining or whether it's drilling for oil. And so the hidden pollution, I guess you could say, in terms of getting the aluminium in the first place, actually is quite high. It's probably higher than what it is for plastics, and you need more of it. Somebody asked about PLA from 3D printing will be increasing and end up in the environment. How bad is it compared to polypropylene? Well, yeah, so PLA is a PLA is a bit of a funny polymer. So polylactic acid is a bio-based polymer that actually isn't biodegradable. So the polymer is biodegradable, but the plastic isn't. So after it's plasticized, it's no longer biodegradable. It does compost in industrial compost heaps to some extent. It does not compost in home compost heaps. So it's in a really weird place in terms of exactly what happens to it further down in its lifetime. It is increasing in production, so it is increasing in use. Compared to polypropylene, well, okay, so polypropylene can be recycled, but we generally don't recycle polypropylene. The reason we don't recycle polypropylene is something I hinted at earlier. The energy required to recycle polypropylene is higher than the energy required to make polypropylene. So if you recycle polypropylene, first of all, it will cost more than to make it because it's so cheap. It's a byproduct, basically, of oil refining. And second of all, you'll increase CO2 emissions by doing recycling. So we generally don't recycle polypropylene. PLA is, at the moment, impossible to recycle. The thermal properties are very bad. It has a very low glass transition. And so it degrades quite readily when it's heated up. And so as a result, at the moment, there is no PLA recycling at any scale at all. And I am among a lot of people who've been trying to develop a chemical recycling route for PLA because it's basically the only option available at the moment. But even those have had mixed success because it's a very difficult monomer because the monomer is lactide rather than lactic acid. And so the recycling often involves an extra step. So how bad will it be, PLA versus polypropylene? I still think err on the side of caution. And so I think at least with the PLA, you know what you're getting. And so if we collect it, even though we can't recycle it, at least we have ways of recovering the material and the energy. Whereas with polypropylene, all you can do is incinerate it. There's no other choice. Someone mentioned about metal as a replacement for plastic. Are the downsides worth it? In my opinion, no. The mass difference between metal and plastic is absolutely immense. I mean, that's an entire order of magnitude, just about, well, depending on the metal, in terms of density. And so the weight requirement is just huge. And so the shipping costs, so the amount of CO2 that's required to transport metal around is really, really high. And also, I've harped on mining enough. You're going to start thinking that this is an anti-mining webinar. But it's the same thing. The more metal we use, the more damage we do to the environment from other industries. Somebody asked about hazardous substances and waste. Yes, this is a huge deal. So especially for waste operators, which is a good point. I don't know if the substances of concern in products database will be useful. I think it's going to depend on exactly how it's deployed. But I've got the slide up still on textile waste, and this is I mean, there are thousands of different compounds that are used to dye textiles. And you know, my eyesight's not particularly good, but you know, there aren't that many colors. I've had boxes of crayons before. I don't remember one with 1,000 different colors in it. But we use so many different dyes because every single company that makes a new material develops a different dye for it. There's absolutely no regulation on this. And so the dyes, the additives that go into plastics and these sorts of things cause a huge barrier in recycling. And as is mentioned, a lot of them are quite toxic. And so just narrowing that field down and saying, okay, let's agree that these are 20 or 50 different dyes that we're going to produce, or additives for plastics, or plasticizers even. Just narrowing that list down, I think, would have an enormous positive impact on how much stuff could be recycled compared to right now. Kieran's asking about the bacteria's recycled. Oh, sorry.
I was just going to say, in the amount of time, maybe just one more question, if that's okay.
Yeah, is there a killer one in here? Yeah, okay, I'll ask this one. It's not necessarily a killer one, but it's my favorite topic to talk about. So can I think of a solution to the problem that everyone seems to see the holy grail in paper as a substitution for plastic, even though it's not better in terms of CO2 and water? Communication versus legal action. I don't think legal action will help here. I think it's a matter of communication. The reason I like this topic is because I have a startup company, or spin-out company now, that's developing pollution-free, so a zero pollution, a low energy way of making cellulose from wood. And so we're trying to make sort of as a technology. I think education or communication is probably the most important thing here. I'm old enough now that I remember when people were attempting to replace paper bags with plastic bags because it was less pollution. And we've sort of forgotten this. And the paper industry has done a very good job of reducing their pollution in recent years. But plastic is such a low pollution material to produce. And the problem is, of course, at the end of life, then we sort of ruin it by throwing it out the window. And so I think people need to be more aware that everyone wants a single answer, right? I mean, if you use paper, it's better than plastic, or if you use plastic, it's better than paper. And it really comes down to actually what you do with it at the end. If you control the material, so if it goes into the proper recycling stream, it almost doesn't matter which one you use. Then it becomes really a question of which is less energy to recycle, and the answer is probably at the moment plastic. But I think where we need to get better control is in our behavior. So we always say consumer behavior, but really it's the whole population. We're all consumers of plastic. And what we really need to do is to stop losing it. So get rid of that 32% leakage stream. And most of the problems with plastic pollution would suddenly go away. And I think that if you want to stimulate recycling technologies, the first thing we need to do is have better collection. If all of the plastic material was brought in for recycling, there would be an enormous industrial push, commercial push to develop new recycling technologies. And I think the rest of it would take care of itself. I'll stop there, Leah. Otherwise, I'll just answer questions for the next hour. It'd be great.
There are quite a lot of questions. So in the interest of time, I think we'll have to end there. But thank you so much to Professor Hallett for such an informative presentation and for getting through so many questions. There were lots of questions, but it's great to engage with everyone, and you got through so many, so thank you very, very much.
Thank you.
This is actually the last in this series, so it was a great presentation to go out on. So a recording of this webinar will be put onto the IMSE YouTube channel very soon, and you can find a link for that in the chat function. I'm just gonna put another link again for that.
Does that mean they'll be able to see my shirt for all eternity?
For all eternity. Once again, I just wanted to say thank you again to everyone who attended, and a special thank you to Professor Jason Hallett for his presentation, and a thank you to everyone who presented in this webinar series. Thank you all very much. Bye.
Thank you.